Hello friends, this is Rajendra Mogal. I welcome all of you for the second lecture on rheology topic. Before actually going in detail about the today's lecture, just we have the overview about your last lecture. So in last lecture we discussed regarding the definition of rheology, viscosity, then importance of rheology in the pharmacy, then concept of the viscosity in that Newton's law of flow. What do you mean by shearing stress, rate of shear, then various definitions like your fluidity, then your kinematic viscosity, intrinsic, reduced viscosity. All these points it is already covered in your previous lecture. Now the next very important point in rheology, it is your classification, rheological classification, or it is also called as the types of flow. Okay, so basically now let us start with your today's lecture. The content for my today's presentation, it is your types of flow or classification of your rheological systems. In that, first it is your Newtonian system, and second it is your non-Newtonian system. In that we are going to discuss regarding the plastic system, pseudoplastic system, and dilatant system. In this today's lecture we will discuss regarding the characteristics of the rheogram, the mechanism that is responsible for their behavior, and finally it is your examples. Okay, so let us start. This is the tree diagram showing the classification of your rheological system or types of flow. So basically rheological system is classified into the two types, that is Newtonian system and non-Newtonian system. Newtonian systems are the systems which obey the Newton's law of flow of fluids. Okay, so already we discussed in your previous lecture, that is a statement of Newton's law for flow of fluids. It is the rate of shear, it is directly proportional to the shearing stress. Okay, so the system which obey this law and follows this law, it is generally referred as the Newtonian system. Examples are simple liquids like your water, ethanol, and your castor oil. The second, it is your non-Newtonian system, simply the system which does not obey the Newton's law of flow. Okay, these systems are called as the non-Newtonian systems. Depending upon the consistency curve, again it is classified into the three types. That is, the first it is your plastic system, second it is your pseudoplastic system, and third it is your dilatant system. First, it is your plastic system. It is also called as the Bingham bodies. The example of plastic systems are your flocculated suspension less than 50% weight by volume concentration, then your butter, then ointment, paste, then gels, and oil paints. Second, it is your pseudoplastic system. It is also called as a shear thinning system. Examples of pseudoplastic systems are the polymeric dispersion like your tragacanth in water, acacia in water, methyl cellulose in water, and sodium CMC, that is carboxymethyl cellulose in the water. And the third, that is your dilatant. It is also called as the shear thickening system. The examples are deflocculated suspension like your starch in water, the kaolin in water, zinc oxide in the water. So first of all, the Newtonian system, that is already we discussed this point. So again we have to just a recall about this. So fluids that obey the Newton's law are called as the Newtonian fluids. What is the statement of Newton's law of flow of fluids? That is, when rate of shear it is directly proportional to the shearing stress, then the system it is called as the Newtonian system. So this diagram it is explained, that is when you take the y-axis, on y-axis if you take the rate of shear, on x-axis if you are taking the shearing stress, then the line you are getting the straight line. Okay, so this diagram indicating that is shearing stress and rate of shear it is directly proportional. Okay, and if you determine the slope of the straight portion of the line, it is called as the fluidity, that is denoted by symbol that is phi. Okay, so it is the reciprocal of the viscosity that already we discussed in your previous lecture. What are the characteristics of Newtonian system? That is, a system which obeys Newton's law of flow of fluids are called as the Newtonian system. As the shear rate increases, the shear stress proportionally it is increases. Okay, so these are directly proportional. When the shear stress, that is the F, is taken on the x-axis and shear rate on the y-axis, then the graphical representation it is called as the rheogram. Okay, it gives the straight line as shown in your figure 2. The rheogram passes, what are the characteristics? That is, the rheogram passes through the origin and the slope gives the coefficient of the viscosity. So if you go to your previous slide, then the line, it is started at the origin, and the value of the slope, it gives you the coefficient of the viscosity, and the reciprocal of that gives you the fluidity. System that follows the slope of the straight portion of the line in Newtonian systems referred as the fluidity. The system that follows this linear relationships relationship are called as the Newtonian fluids. Examples are of Newtonian system, that is simple liquids like your water, castor oil, ethanol, glycerin, olive oil, chloroform, solutions of the syrup, very dilute colloidal solutions. Next point, it is a very important, that is non-Newtonian flow. Okay, so some fluids, mostly the dispersion systems, not obeys the Newton's law of flow called as the non-Newtonian flow or non-Newtonian systems. Depending upon the type of the curve, the non-Newtonian fluids are further classified based on the various consistency curve when the material it is analyzed in the rotational viscometer. Okay, so this classification is totally depends on the consistency curve. Consistency curve means that is your rheogram. Okay, so depending upon the shape of the consistency curve, these are the three classification of the non-Newtonian flow. So first one, it is your plastic system, which is also called as a Bingham bodies. Pseudoplastic system, which is also called as a shear thinning system. Dilatant system, it is also called as a shear thickening system. Why these synonyms are given, that we are going to discuss in the next section of this lecture. So let us start with the first, and that is your plastic system, which is also called as the Bingham bodies. First of all, the characteristics of the rheogram. The curve does not pass through the origin. See the figure 3, that is your curve. It is not started at the origin. Second, the substance, it is initially behave like a elastic material and fails to flow when less amount of stress it is applied. So elasticity, it is a property of the solids. So elasticity and plasticity, what do you mean by elasticity and what do you mean by plasticity? So elastic nature means, that is, if you apply the force onto your material, then deformation means shape and size of the material, it will change. Okay, and upon removal of the stress, again the material regain to its original shape and size. That material, it is called as the elastic material. And upon the application of your force, if the permanent deformation if it is occurs in the solids, then it is called as the plastic system. Okay, so like elastic system, like you take the example of your rubber. So if you stretch the rubber, then the shape and size of the rubber, it will change, and again upon the removal of the force, again rubber acquire its original shape and size. That's why we are saying that is a rubber, it is elastic in nature. So similarly, this plastic flow also, it is behave like a elastic material, so that's why it will fails to flow at the lower shearing stress. Next, when you goes on increasing the stress, that is a further increase in the stress result in the non-linear increase in the rate of shear, which progressively gets linearized. Okay, so initially after that, you can see that is after application of certain shearing stress, then the curve, it is non-linear, and afterwards again it is completely a linear portion. So you can see that is initially your system, it is not flowing. After that, after some value of the shearing stress, your rate of shear, it is increases, but it is a non-linear. And after that, after one particular value, then upon increasing the shearing stress, the rate of shear, it is proportionally increases. So these are the three parts of this particular rheogram. When the linear portion, it is extrapolated towards the x-axis, the point of intersect on x-axis, it is called as the yield value. Now let us, you can see from the diagram, that is the linear portion, when it is extrapolated towards the x-axis, the point of intersection, it is called as the yield value, that is denoted by small f. It is a very important point that we are going to discuss in subsequent section. So the plastic flow resemble to Newtonian flow above the yield value. So what is the conclusion from this? That is, above the yield value, your system, your plastic system, it is behave like a Newtonian system. Now again, if you see in this particular diagram, that is the value of the slope, it is equals to mobility. It is mentioned in this particular diagram. While in case of your non-Newtonian system, the value of the slope, it is corresponding, or it is resemble to your fluidity. So In this case, in case of your plastic system, it is called as the mobility, and this mobility again it is resemble to fluidity in case of your Newtonian system. Second, what is the next? It is your what is the mechanism for the plastic system. So the common example of the plastic system, it is your flocculated suspension. So flocculated suspension means that is these particles are aggregated by the weak van der Waals type of forces. Okay, so magnitude of this van der Waals type of forces, it is a very weak, and slight application of the force, it is sufficient to break the contacts. Okay, so now let us discuss the mechanism. Such phenomena, it is generally exhibited by the flocculated particles. Floccules are the aggregation of the particles with interparticular contact at the rest. Okay, so you can see in this particular diagram, that is a flocculated suspension. The characteristics are given. There is an aggregation between the particles, and these particles are aggregated or adhere to each other due to the weak van der Waals type of forces. Now what will happen? What will happen when you apply the stress? When the stress it is applied, the interparticular contact broken, and each particles gets separated and behave individually. Already we discussed that is the magnitude of the van der Waals forces, it is very weak, and if you apply the slight amount of the force, then this force it is sufficient to break the interparticular contact. So that is above the yield value, it is represented, that is above the yield value, you can see that is the interparticular contact, it is broken, and now each and every particle it is completely separated. This is the yield value, and it is represented by the force of flocculation. So concept of the force of flocculation, it is very important in case of manufacturing of the flocculated suspension. Okay, so how much force it is required to break the interparticular contact? So for the redispersibility of your suspended particles, for that purpose the force of flocculation, it is very important, and accordingly the addition of your flocculating agents, it is in the manufacturing of the suspension, it is decided. Okay, so this force of flocculation concept, it is important in case of your manufacturing. Now once the yield value exceeds the shear stress, it is directly proportional to the rate of shear. Okay, so now above the yield value, as you increases the shearing stress, then it is directly proportional to the rate of shear. So this is the statement of your Newton's law. So what is your conclusion from this? That is above the yield value, your plastic system, it is behave like a Newtonian system. Okay, so like in this last section of this particular diagram, that is above the yield value, if you increase the further stress, if it is applied, then the flow inside the system, it will occur. Okay, mathematical derivation, that is a material exhibit the plastic flow, also called as the Bingham bodies, in honor of the Bingham, who carried out the many studies on such material. Okay, so the Bingham equation, it is U is equals to capital F minus small f divided by the G. In this equation, that is the F, it is the yield value, U, it is the plastic viscosity. So in case of your instead of saying it is simply as a viscosity, the plastic systems, it is the viscosity of the plastic system, it is called as the plastic viscosity. The slope in the rheogram, it is termed as the mobility. Examples are, that is a flocculated concentrated suspension less than 50% weight by volume, then your butter, then your ointment, then your paste, then your gels, and finally it is your oil paint. Okay, so these are the example of your plastic system. Next, pseudoplastic system, that is a second type in non-Newtonian systems. Pseudoplastic systems are also called as the shear thinning system. Thinning means that is the consistency, it will be decreases. Okay, so that's why it is called as the shear thinning system. First of all, the characteristics of this rheogram, the consistency curve begins at the origin, and with increase in the shearing stress, the rate of shear also increases, but it is non-linear. You can see this particular figure 4, in that the curve, again the curve, it will begin at the origin, and the entire curve, if you see, then completely it is non-linear. Like in case of your Newtonian system, it is completely linear. In case of your plastic system, initially it is superimposed over the x-axis, then it is a non-linear segment, and finally it is a linear segment. But in case of your pseudoplastic system, the entire curve, it is completely a non-linear, so that the viscosity of your pseudoplastic material cannot be expressed by the single value. Okay, so that's why the entire curve it is most satisfactory. You cannot say that is this is the viscosity. So entire curve it is required to express the viscosity of pseudoplastic material. Examples: generally the polymeric dispersion in water or any other suitable solvent is generally exhibit the pseudoplastic flow. Like example, tragacanth in water, sodium alginate in water, methyl cellulose in water, and sodium CMC, that is sodium carboxymethyl cellulose in the water. Mechanism: under normal conditions, the polymeric molecules are randomly arranged in the dispersion. So polymers are, that is this word it is derived from the two words, that is a poly means many and mers means it is units. Okay, so when many small units they will join, whether it is in the linear segment or in the branch segment, then it is called as the polymer. Okay, so the characteristic of the polymer you have to remember. First it is your, there are in case of your branch polymer and in case of your cross-link polymer, the two characteristic it is very important. First it is your, it is characterized by the long axis, and second it is your by the short axis. Okay, in case of your linear polymer there is only a long axis. In case of your branch there is a long axis and short axis, and again in case of your cross-link polymer again there is a with the long axis and there will be a short axis. Okay, so what is this it is very important for understanding of the pseudoplastic system, the mechanism of the pseudoplastic system. What will happen, that is on application of the force, that is under normal conditions, that is a given, that is these long axis of the polymers, they are randomly oriented. So when there is a randomness, randomly oriented, then in that case such kind of a structure it is offers a more resistance. The characteristics are given below the figure. See the figure, that is at the rest, that is random arrangement and the solvents is bound. Now to understand the concept of this, let us take the example, that is suppose say if you take the example of your curly hairs, then might be your, this is your observation or you heard about this, that is the hairs are randomly oriented, so that's why such kind of your structure it offers a more resistance while comb. Okay, so same concept it is applicable in case of your pseudoplastic system. So when your material it is at the rest, the long axis of the polymers they are randomly oriented, and such kind of your structure it offers a more resistance. Now what will happen? What will happen when you apply the stress? On application of the force, the molecule starts to arrange in the direction of force applied. Okay, this leads to decrease in the internal resistance of the material. So when you apply the stress, the long axis of the polymer starts aligning in the direction of force applied. Okay, suppose in this case we are applying the force in the horizontal direction, so that's why you can see the in the right hand side of the your figure, that is upon application of your stress, the long axis of the polymer it is horizontally it is oriented. Okay, and what are the characteristics of this? That is during the flow the polymer long axis align in the direction of the force applied and water it is released. Okay, so now when the long axis of the polymer align in the direction of the force applied, such structure it is offers the less resistance. Again, to understand this concept, again go back to your next slide. That is a take the example we have taken the for understanding of the your randomness, we are taking the example of your curly hairs. Now to understand the concept of the this straight long axis. Okay, when your long axis of the polymer align in the force of the direction of the force applied, then what will happen? Take the example that is your straight hair. So in case of your straight hairs, the hairs are oriented in the one direction. So and such kind of your structure it offers a less resistor while comb. Okay, so again this is your observation routine examples, that is your curly hairs they are offering it offers a more resistance, while your silky and straight hairs they are offering the less resistance. Okay, so by means of this we can understand the pseudoplastic system. In addition to above mechanism, though this is the minor mechanism, that's why we are not majorly we are focusing on this. The first one it is a major mechanism. In addition to the above mechanism, the solvent associated with the polymer molecules will liberated, and which leads to decrease in the concentration due to dilution. In first left hand side of the figure you can see that is your blue spheres. these are the solid molecules which is attached whether to the short axis or long axis of the polymers. So these solid molecules, it is associated with the polymeric molecules. On the right hand side, if you see, then in that case these molecules are gets separated. Okay, so gets separated from the whether from the long axis or from the short axis. That results into the slight dilution of the solution or mixture. This is the minor mechanism, so that also leads to the decrease in the consistency or decrease in the viscosity. So at this particular stage, the material allows greater shear rate on progressively increase in the shearing stress. Okay, so at this particular, when all the long axis of the polymer align in the direction of the force applied, your solid molecules gets liberated. Such kind of your structure offers the less resistance. So if you increases the shearing stress, the rate of shear, it is significantly, it will be increases. So rate of shear increases means, that is, rate of shear, it is inversely proportional to the viscosity. Rate of shear increases means viscosity, it is decreases. Viscosity decreases. So that's why that the system, it is called as the shear thinning system. Okay, so this is all about your pseudoplastic system, the mechanism. Now the next is your equation. The equation for pseudoplastic material is, that is, F raised to n is equals to eta dash into g, where the n is the number given to the any exponent and n dash, it is the viscosity coefficient. Okay, so terms are same. F, it is your shearing stress, g, it is your rate of shear, and eta, it is your viscosity coefficient. Only slightly this equation, it is modified for the pseudoplastic system. For pseudoplastic fluid, the value of this exponent n, it is generally higher than the 1 and goes on increasing as the flow becomes increasingly pseudoplastic. Okay, so for pseudoplastic system, this value of the n, it is generally higher than the 1, and if your system becomes more pseudoplastic, then the value of the n will be increases more than 1. Take the log. Now, so derivation of this equation, that is, take the log to the both the sides of above equation. N of log of f is equals to log of eta dash plus the log of g. Now rearrange the above equation for by taking shift log g towards the left hand side. So log g is equals to n log of f and minus log of eta dash. This equation 3, it is represent the straight line. That is why you are converting it into the logarithmic form. Logarithmic equation, why it is required? Because the pseudoplastic curve, the entire curve, it is a non-linear, so that's why we are not getting the useful information or useful data. So the equation, when it is converted into the logarithmic form, it gives you the straight line, and from the straight line we will get the useful data. So this is the equation 3, it is applicable for the pseudoplastic system or shear thinning system. Now the last, that is your dilatant flow. It is also called as a shear thickening system. As the name implies, that is the thickening. That is, upon the shearing, the consistency of your material goes on increasing. Now, what is the mechanism and what are the rheogram that we are going to discuss? First of all, the characteristic of the rheogram. Sometimes the increase in the resistance to flow with increase in the rate of shear occurs. Okay, so in case of your pseudoplastic system, as you increase the shearing stress, the rate of shear, it will be increases. Okay, rate of shear, it is increases, but in this case, that is that is a increase in the resistance to flow. That is in a dilatant system, that is, as you increase the rate of shear, the consistency of your material, it is increases. Okay, so material becomes more thickened, so that's why it is called as a shear thickening system. When such material is sheared, on increase an increase in the volume occurs, so it is called as the dilatant. Okay, so dilation means that is your expansion of system, it will takes place. That's why this system, the name it is given, that is a dilatant system. So volume of the material, it is increases. These systems also called as the shear thickening system, as the viscosity increases with increase in the rate of shear. Okay, so in case of your pseudoplastic system, as you increase the shearing stress, the viscosity, it is a decreases, while in this case, as you increases the shearing stress, the viscosity, it is increases. That's why pseudoplastic system are called as shear thickening system, while dilatant systems are called as the shear thickening system. Now the next is your what is the mechanism? When dilatant system it is at the rest, the molecules are closely packed. See the diagram towards the left hand side. That is, the characteristics are given, that is a close packed particles. The blue color particles are there and the gray color represent the your fluid. Next, it is your minimum void volume. So what do you mean by void? First of all, that is a interparticular spaces that is present between the particles, that is called as the void spaces. Okay, so in this case, that is you can see from the diagram, that is the particles are very close to each other, the void spaces are very less, and again the next it is the characteristic it is given, that is a sufficient vehicle. Now sufficient vehicle it is there to fill all these particular interparticular spaces or voids. Okay, so now why it is important, such kind of a characteristic it is important, that we are going to discuss in later section. Next characteristics of this state, it is relatively low consistency. Now why such kind of your structure it is having the relatively low consistency? Because that we are going to discuss in this point, that is a minimum void volume is present and amount of vehicle it is sufficient to fill the void. Okay, so already we discussed that is a minimum void spaces are there, and liquid, that is it is a amount of the vehicle it is a sufficient to fill the void spaces. Under this particular condition, the particle moves related to the one other, so that low consistency. So now what will happen, that is like when the particle they will slide over the each other, they will move related to the each other, then in that case your fluid now act as a lubricant. So that's why these particles they can slide or they can slip over the each other easily. Like suppose the lubricant we are adding the lubricating oil in your gearbox, that is to decrease the friction between the particles. Similarly in this case also, the fluid which decreases the friction between the particles, that's why these particles they can easily slide over the each other. Now obviously such kind of your structure it offers a less resistance, and less resistance means relatively low consistency. Now what will happen, that is when you apply the shearing stress, then what will happen, that is when shear stress it is applied, particles are opened and the bulk of the system expand, means void volume significantly is increases. Okay, so now upon the application of your when the material is sheared, then what will happen, that is the expansion of the system it will takes place. You can see in the right hand side of this particular diagram, that is interparticular distance it is increases. In first diagram the particles are closer to the each other, while in the second diagram towards the right hand side the distance between the particles it is quite high. Now what will happen due to that is as the interparticular distance it is increases, then what will happen, that is now the amount of the vehicle it is insufficient. As this in previous that is in a previous section, in previous diagram, at the rest position before shearing, the lubricant it is the amount of the vehicle it is sufficient for the lubrication. Now as the system the expansion of the system it will takes place, the amount of the vehicle it is remains same. That's why now the amount of the vehicle it will be insufficient to lubricate, and therefore that structure it will develop the resistance to flow. And if the structure it offers a resistance to flow, means that is your viscosity it is increases. So that's why in case of your dilatant system, as you sheared your material, as you increases the rate of shear, the consistency of your material goes on increasing, the viscosity goes on increasing. That's why it is termed as the shear thickening system. What are the examples of dilatant system? That is a suspension containing the high concentration of your solid, generally more than 50% weight by volume of the small deflocculated particles. Examples: suspension of the starch in the water, then kaolin, that is a 12% weight by volume in water, zinc oxide 30% weight by volume in the water. Same, that is just to understand the concept of your dilatancy, this diagram it is shown. That is in first side, that is a starch solution in the water at the rest position we have taken. The initial volume, suppose say it is a 50 ml, without agitating, without stirring this solution. Okay, so note the volume it is noted as the 50 ml. Now when you start agitating this solution, start stirring this particular solution, then due to the dilatancy behavior, the expansion of the system, it will takes place. Now you can see on the right hand side, that is a volume. Now it is equals to 60 ml. So initially it is a 50 ml, now it becomes 60 ml, means volume it is increases. That's why these systems are called as the dilatant system. Okay, so this is all about your today's lecture, today's topic. So in your today's topic, we discuss regarding the classification or the types of the flow, that is a Newtonian system and non-Newtonian system. Non-Newtonian systems are also classified into further classified into three types, that is plastic system, pseudoplastic system, and your dilatant system. So plastic systems are also called as the Bingham bodies. Then next it is your pseudoplastic systems are also called as a shear thinning system, and dilatant system, the third type, that is a dilatant system, are also called as the shear thickening system. Just remember the examples. The examples may be asked in your competitive examination. That is for your plastic system, you have to remember the example. It is your flocculated suspension. Okay. Next it is your the pseudoplastic system, polymeric dispersion. So any polymer, when it is dissolved into the aqueous media or any other solvent, generally it exhibits the pseudoplastic system. And the last, it is a dilatant system. That is your, you have to remember, that is a deflocculated suspension, and concentration it is generally more than 50%. Okay, these are the points you have to remember in your today's lecture. The question it may be asked in your, this point it is very important from the university exam point of view, from the competitive exam point of view. Okay, so the question it may be asked for, that is explain the various types of flow or rheological classification with its mechanism, with the rheograms and examples. Okay, so this is all about your today's lecture. In my next presentation, we will discuss regarding the next point, that is your very important point again, the thixotropy. In thixotropy, we will cover the definition, the meaning of the thixotropy, the mechanism for thixotropy, then measurement and its application in the pharmaceutical sciences. Thanks for watching this video. If you like this video, please like and subscribe my channel for more related videos.